All right, and here we are for Chapter 6, Managing Raster Data. So rasters are sort of my bread and butter, like I've mentioned several times. And being in the geosciences, we have a tendency to use these quite a bit because we're mapping natural phenomena from elevations to watersheds, soils, all kinds of stuff like that that would be applicable to the geosciences. That's not to say that you don't use vectors, because you absolutely do, but a lot of at least my time is spent in raster world. So we're going to look at all the various aspects of rasters, kind of what you could do with them and how to process them, and other fun techniques. All right, we've mentioned this before, and it bears repeating. Rasters are set up a bit differently than vectors in the sense that you have to know, the program has to know what the quarter XY location is there, and then the number of columns and the number of rows, and then the spacing of, how big each cell is. So a raster stores their XY array values in pixels, or we call them cells, and then it's georeferenced to Earth's location based on that corner XY location, and then again the number of rows and columns. This way it knows where to put it on Earth. So each pixel contains one numeric value, and that's what makes it very, very, very different from, let's say, a vector attribute. Because in vectors, you can have numerous columns with all kinds of data in it. And we've already seen that. So let's say you have a polygon of a county, and within that county polygon, you could have, demographic data, population, area, all kind. You could have a whole bunch of columns. However, in raster world, you get one and only one value per cell, which is really simplistic and nice to deal with in terms of you know exactly what measurement you're getting. It also has a few sort of downsides in terms of processing, not necessarily because it's more difficult, but just because you need a raster for every single phenomena that you're trying to map or use with geoprocessing tools. We'll get more into that in a bit. So every value in each square represents some property, whether it be elevation, rainfall, temperature, a soil characteristics, a land use. There's all kinds of rasters that can be used. And those numeric values can be either integers or floating point numbers, depending on the type of data you're using. So, like I mentioned, unlike polygons, you get one and only one attribute. And what you'll see is that means you have to create a raster for every phenomena you're trying to map. So if you go and look at that poster outside my office, I used 11 different rasters to get the final 12th one. So you need one raster for every single thing you're trying to map, which again isn't a bad thing. So looking at the cell values, you can see, for example, here you have a value of 1 in the upper right corner here, and each cell in this case is 30 meters by 30 meters, and that's what we would call the resolution. So if I say a 30-meter DEM, or digital elevation model, that's what it is. Each cell value is 30 by 30 across, giving each cell 900 meters of area. Now, 30 meters by 30 meters is perfectly fine for a lot of uses. And for many years, that was sort of the de facto standard. Now, 10 meters has become sort of the de facto standard based on the fact that the data is out there, it's freely available, and with the computers being as powerful as they are, running these tools on a 10-meter DM is not that big of a deal in terms of CPU processing. So why use rasters? Why can't you just use vectors for everything? Well, technically you probably could, but there are reasons why rasters are just easier to use. They're better at storing certain kinds of data. And for example, any continuous surface, like elevation, precipitation. So that's why you would use rasters. Um, the analysis is often faster than vectors. And there are some trade-offs though. However, you don't get the coordinate precision that you would with vectors because there's a mathematical formula, so to speak, where to put everything on a map. The high precision comes as high storage costs, meaning the higher the resolution of your raster, the space to house that raster goes up like exponentially. And you cannot store multiple attributes. So one raster equals one attribute. So if I have elevation raster, that's all you get is elevation. If I have land use, that's all you get is land use. So it has its pluses and minuses. Conceptually, it's really easy to understand, especially when you're doing things like what's called overlay, which we'll get to later in the semester. It's just easier to understand because the math becomes cell by cell. Again, we'll get more into that later, but conceptually, it's pretty easy to understand. So here's some examples of some rasters. So in box A there we have digital elevation model. You'll hear me say DEM all the time. It's just, like I said, being in the geosciences, it becomes a type of data set that you're going to use over and over and over. So each cell value, it's, a DEM, each cell value contains one and only one elevation value, and put them together, you get sort of this continuous surface of what the real world looks like. We'll use them all semester long, um, pretty much. You have color aerial photography. We're not going to do a whole lot with that other than a couple things in the tutorials, but there are some aspects of using color photography that you can use for some what's called remote sensing applications. You have in box C land use categories. So that's a different kind of raster known as a discrete raster. You have primary, secondary, and primitive roads. I'm not exactly sure why this is being used as an example, but it's there. I don't use it that way, very rarely, but okay. A scan topo map or a DGR or DRG, excuse me. These are just, think of it as USGS topo maps sort of laid down in the background. There's not really much you could do with them other than it's basically a pretty picture in the background. Um, and then finally, ArcGIS Online base maps, which are super easy to use. However, again, just kind of like the DRGs, you can't do much with them other than it gives you sort of that base map, a sense of place wherever you are. Now, there are two main kinds of rasters. We discussed this briefly. There are continuous rasters and discrete rasters. Most of what we do is the continuous raster type, um, where it stores numeric values that can be measured, things like elevation, precipitation, temperature. And those are typically on some type of numeric scale. So obviously with temperature, you would have, assuming Fahrenheit, you'd have, measures above or below zero, whatever, or elevation, mostly above sea level, but some places below. And then you have imagery, which is just satellite photos, which are typically based on a brightness scale, on a scale between 0, which is all black, and 255, which is all white. So it's kind of a grayscale imagery, or a combination of color bands. We don't do much with those. However, they can be used for things like digitizing vectors. So you could see in box B, if you could zoom in if the resolution is high enough, and you could start to actually trace or digitize, let's say, building footprints. The other type of raster that we will see once in a while is what's called a discrete raster. And it's a little bit different than continuous rasters in that you can have lots of area of the same value. So things like land use, where you have large chunks that might be considered urban or large chunks that might be considered agricultural. So a lot of discrete rasters are converted from vectors, points or lines or whatever. And unlike continuous rasters, you can actually have an attribute table as long as you don't have too many different and unique values. You can actually have an attribute table for a discrete raster. Again, it only stores one attribute. So if you have a land use raster, that's the only thing that you'll see in the attribute table. But it's still, with these, oftentimes you can actually have an attribute table that goes along with the raster itself. So maps based on vector data can be represented as a raster tile, which is similar to taking a picture of a map. So you have both raster and vector data sitting on one map, and you can kind of take a snapshot of that in order to sort of share it. So like the USGS topo maps, that has both continuous surfaces on it in terms of elevation, but it also has points and lines and everything else on it, and it's all on one map. So the ArcGIS online based maps also have that same similar feature where you have all these complex vector data on top of layers and symbols, but they're sort of used as a continuous single map raster background image, so to speak. So that allows you to take very complex sets of data and display them very quickly without having to do all the individual layers. So the resolution of a raster is based on the length and width of each cell value. So if I say we have a 20 meter, or excuse me, a 10 meter DEM, the length is 10 meters and the width is 10 meters for each cell. Now, the idea with this is that you're limited, the precision of a raster is limited by the resolution. You can't create more resolution by making the cell size smaller. You can downgrade. I can go from a 10 meter to a 30 meter. That's just sort of subdividing or grouping cells into larger cells. But you can't go from 30 meters to 10 meters. You don't gain anything by doing that. And as for storage requirements, this is where file size can play a role. Rasters can get very big in a hurry. The storage requirements increase by the square of the resolution. So you could see that a 10 meter rows is 81 times more, the file size is 81 times bigger than a 90 meter raster. So these files get really big really quick, especially when you get into things like LiDAR, where you're at 1 meter or even sub-meter resolution. Those files get into the gigs and even terabytes in a hurry. So how do you actually serve high resolution rasters? Well, it's done by having multiple layers with different resolutions. So rather than just have one single copy of a raster, they'll build successive layers at different scales in order for you to quickly be able to view them without bogging down your computer or having lag time in terms of zooming in or out over a network. And this is done with what's called pyramids. So raster pyramids are built to speed up displaying rasters. Like I said, rasters can get very big in a hurry. So copies of it at successively lower resolutions are created in order to quickly be able to zoom in or out and without a lot of that lag time going on. However, you are increasing the size of the raster in terms of file size by about half in order to do this because you're creating multiple copies of it. However, I've always told my students, if the program ever asks you, do you want to build pyramids, go ahead and do them. The computers nowadays are so fast that very little of this is even noticed anymore. So you're only doing yourself a good service by building the rasters to make zooming in or out much easier. So an added step with rasters that has to be taken into account is something called resampling. And that's typically done most of the time to either line up cells or when you project a raster into a different coordinate system. So if you are doing raster analysis, you want all of your cell sizes to be identical. You want them all to match up. So therefore, you have to specify how you want that process to take place. So if you look at the graphic here, the original is in 30 meters. We're going to kind of sort of downgrade it to 40 meters. So in order to do that, it runs an algorithm in the background, sort of a smoothing algorithm that creates this new cell size. This type of process is used a lot in image manipulation, like let's say in Photoshop. These are smoothing techniques. You're creating a different cell size, which forces you to sort of take the average or a smoothness over the image soften it, so to speak. Now there's several different ways to do this. So block resampling, this is one of the first ways to do that, groups pixels and determines the new value using a statistic. This pyramid uses block resampling with majority. So it's going to take all of the cell values that fall in the new grid system and take the majority rules sort of approach. Again, these methods are all found in a drop-down menu. So you don't have to like actually um, like do any math with this. You just have to know which type of statistic you're looking for. There's minimum, there's mean, maximum, and majority. And you can look up online in ArcGIS help to figure out which one does what and what's the best way of doing this. So for example, let's say the mean, if we're using the mean, that is just like the other ones, it's a smoothing algorithm. You're going to average out all of the values, which means you're going to lose visual resolution. It's definitely going to smooth out the image. So you may not want that as much, but you can also look into things like minimum or maximum to see how the images look after the fact and see if that's what you're trying to get at. When it comes to resampling rasters, there's three big main types. Now, the differences between all of these three are, they're negligible in the sense that the first one is used for one specific and the second two are used for something else. And what I want you to get out of this slide is that there's two kinds of rasters that we discussed. There's discrete rasters, okay, which have large areas of a single value like land use. And then there's the continuous rasters like a DEM or temperature or precipitation. And if you look through the explanation here, the nearest neighbor resampling is best used with categorical or discrete data. It's the fastest method for any type of raster, okay? However, the second two, the bilinear and the cubic convolution, require more computing power, but they are more designed for continuous surfaces, things like elevation, precipitation, and stuff like that. So what I tell my students is when you're going to resample a raster, if it's a discrete raster, use nearest neighbor. If it's a continuous raster, use bilinear or cubic convolution. Take your pick. It doesn't really matter that much. Um, Bilinear is sort of the default for continuous rasters. Um, but the idea is just to make sure that you're using either bilinear or cubic for continuous rasters. So why do we resample? Well, when you go to project, or like I mentioned earlier, when you need all of your cell sizes to match up, if you're going to do analysis with rasters, usually involves what's called overlay, where you're stacking rasters on top of each other and doing some type of math that drills down through the cells, cell by cell by cell. In order for that to work properly, you need all the the cell sizes to match up. If I have a 10-meter DEM, I want it to match up with any other raster that I'm using in my calculation. So we need to resample those things. Now, you can't go from, like I mentioned, 30 meters to 10 meters. You don't gain any resolution that way because you're not adding any information in that process. You can downgrade, let's say going from 10 to 30, but a lot of times what this is I tell my students, let's say for example, working on your final projects, if you're going to use a 10-meter DEM, you will set up your environment variables. There's one called cell size to match that. And what that does, it kind of alleviates having to do this manually. But usually you're going to dictate what cell size you're going to use by like whatever you're starting with. So if I'm starting with a 30-meter DEM, I'll keep all my cell sizes 30 meters so they all match up. If I'm using 10 meters, I'll keep it 10 meters. Now, when I did my terroir study stuff for the ledge, the big poster that's sitting outside my office, the research that I kind of modeled that on used 9-acre plots because 9-acre plots were about the minimum viable plot for an economically viable vineyard. So I did the math on that to figure out what that is in square meters or square feet, I forgot off the top of my head. And then I made my cell size that. And again, that's just to kind of, that was following the methodology found in the literature. But for you guys, if you kind of let the DEM dictate what you're going to use. So if I have a 10-meter DEM, I set my environment variables, which we'll get to later, but you'll set your environment variables to match the cell size of your DEM or your whatever raster you have. And then and you could tell it to always use this nearest neighbor or bilinear or cubic convolution, and you can have it project it where you want to. So all of those things put into the environment variables will alleviate you having to do this manually every time you create a new raster file, which you will do because every tool you generate or every tool you run generates a new raster. Now, every once in a while, you'll see what something. If you look into the metadata, you'll look, and some of the tools that you run require you to know what the pixel depth is. All right, so pixel depth is the number of bytes used for each pixel. The higher the number, the more values you can have um, in terms of like uh, accuracy. So, like for example, uh, an 8-bit pixel can only have values 0 to 255. So that would be a black and white image. 0 is black, 255 is white. 16-bit is stores up to 65,000 different values. All right, and then you go up from there. Okay, so for a lot of purposes, a lot of what you're going to see, if it's a black and white image, you'll see 8-bit. And if you see lots of colors, it's usually 24-bit. And then if you're using any kind of continuous surface, they're almost always 32-bit floating point rasters. This information is found in the properties of the raster, and you're going to need to know this when you go to, let's say, project a raster, because it's part of the tool that you need to run in terms of knowing that information. Is it 8-bit signed, 16-bit unsigned, 32-bit float? You need to know that, so that's in the properties of each one of the rasters, or possibly, or in the metadata. Now, a band is a single raster, and for most things that we do, we're going to look at a single raster, a DEM, or a grayscale image, or a discrete raster. However, you can get what are called multi-band rasters, where you actually have, let's say, a satellite image that can have up to 7 different bands of different wavelengths of light. You have the red band, the green band, near infrared, ultraviolet, all those things. Um, you can change those bands to manipulate them to get at specific types of information. This is what we call remote sensing. Now, we don't do that in this course per se. We'll do a tiny bit of it just in the tutorial, just so you can kind of see. But multi-band rasters contain sort of an array of rasters, and then all in the same number of columns, rows, and resolution, and you can mix and match the different color schemes to create all kinds of interesting results. So when you're displaying multi-band rasters, you can change the bands that have the different wavelengths of color. So we have the natural colors, the reds, greens, and blues. You have false colors, things like near infrared, red, blue, and then band 7, which is near infrared and blue. So the different combinations of these give you different things. Some will show natural color, like in picture A here. Some will show this false infrared, and what that's good for is highlighting things like urban sprawl and uh, uh, glacial snow kind of stuff. And then you can also kind of flip that and look at vegetation, the sort of the perceived health of the vegetation in an area. Again, what's really nice about this is that in ArcGIS, using these different bands, they're all just little drop-down menus. We don't cover remote sensing in this course. It's a whole nother science all onto its own. There's a great class that's offer it over in geography, all about remote sensing, and they use programs that are designed for things like ERDAS or Adrizi. Um, GIS does a little bit of it, but it's not what its primary function is for. There's better programs for that. Another thing that you'll run into is compression. Now, I bring this up. I was deciding whether I wanted to keep this slide or not, and all of those numbers up at the top of the slide, that's not important. What I want you to understand is a lot of different file types that you're used to every day are compressed. Every picture you take on your phone is a JPEG. That's a lossy format. Okay, so it takes images and kind of like plucks out part of it, part imperceivable parts to you and I with the naked eye, but it does that to keep the file sizes lower. All right, so there are some raster formats that are heavily compressed. One that comes to mind is a proprietary format called a Mr. SID file, and that's what it's called, Mr. SID, SID. And these are highly compressed. I mean, it's a proprietary algorithm, super compressed, high resolution images. They're really cool. I made the mistake once many years ago of trying to uncompress it, and yeah, don't do that. I had to reboot my machine. But so you have to be careful that you know what you're getting to and understand, is the format I'm trying to use worth the, can I use a lossy format, or do I want to keep as much of that resolution as possible? Normally you want to try to keep as much detail as possible, but there are times where the size of the file just becomes too cumbersome, and then you just have no choice at that point but to either chop it up into smaller pieces, or just bite the bullet and sort of downgrade it to something else. So there's data and there's picture rasters. I typically try to avoid picture rasters because that's all they're good for. They're literally just a background image. So data rasters actually store values, things like elevation, aerial imagery, land use. Okay. Whereas picture rasters store color values and cannot be analyzed in any way, shape, or form. Things like, the USGS topo maps or any type of, ArcGIS base map. It's important to know to understand the difference. People like to put these base maps on their maps without realizing you literally can't do anything with them other than zoom in or out or pan around them. What we typically are going to use and what you would use in the real world are data rasters that have actual intrinsic data in it, whether it be aerial or, excuse me, elevation, precipitation, temperature, soils, aerial imagery, all kinds of stuff like that. Those are the vast majority of the type of rasters that you're going to use. If you have the wherewithal to use a base map, it's not a bad thing. It's just you just have to understand that literally all that is a pretty background. Think of it kind of like a wallpaper. That's almost what it is. So just like vectors, we have to kind of watch our P's and Q's with raster coordinate systems. And just like vectors, do not ever do raster analysis when the data is still in Latin long or a GCS. Because again, the math doesn't work out correctly. Sometimes the tools will run. However, you're just going to get really weird exponential numbers because the numbers don't add up, especially going north to south, because the parallel lines on the Earth get closer together as you go towards the poles. So you have to make sure that you use a two-dimensional planar coordinate system. Also, you have to make sure the coordinate system is dictated by the functionality you need it for. If you need it to preserve areas, then choose a coordinate system that will preserve area or preserve distance to ensure that everything you're doing is up to snuff, so to speak. Now, I kind of waive that rule a little bit for your final projects because, again, at the county level, there's very little distortion in any way, shape, or form. So you really don't have much to worry about in that respect. So like I mentioned before, projecting rasters is a completely different tool However, it's very similar to the regular projection tool for vectors with the added step of having to do the resampling. So if you look at the tool here, you can see here's the input tool, here's the input raster, excuse me. That's what it's called going in. This is what we're going to call it going out. Here's the coordinate system we're going to use. If there's a geometric transfer or geographic transformation, it would be in there. And then down near the bottom here, you have the resampling technique. You have to put something in there. Okay. Now, if you set your environment variables, that'll already be filled out for you. That's one of the beauties of doing your environment variables, is to make sure that everything here is already filled in for you. But if we're going to 10 meters, you could set the output to 10 meters here. This is nearest neighbor, so I would use that if I'm using a discrete raster, or I would use the drop-down menu here and change it to bilinear or cubic convolution. Okay. Now, if you go out to the real world or out to the web and get rasters, let's say from the USGS, they usually almost always are in geographic coordinate systems. Okay, why is that? Because the USGS doesn't know what coordinate system you're going to need for your project. So they just leave everything in latitude and longitude and leave it up to you to actually project that particular raster, which is a good thing. Because again, typically when you download a raster, unless if you downloaded it perfectly, you'll probably have to extract it and then you'll probably have to project it as well. So having it just in Latin long is just easier to deal with in the short term in the beginning, and then you just process that particular raster to get it where you need to go in terms of down to your area of interest and the coordinate system you plan on using. Sometimes what you'd like to do is take some random image, let's say from the internet, and bring it into GIS world. And you can do that with what's called georeferencing rasters. And what this allows you to do is take an image and using control points, you can actually sort of, what the old term is called rubber sheeting. You can kind of stretch this random, let's say JPEG image to give it real world coordinates and bring it into your GIS. Now, this takes a little bit of practice, but it's not hard by any means. And there's three different transformations: the affine, the second order polynomial, and the third order polynomial. And they get progressively more sort of aggressive in terms of how much actual rubber sheeting is taking place. So you add a bunch of points from the image to your GIS, and then you look at what's called the residual or the root mean squared, and you want to try to keep that number as low as possible. What that does is give you sort of an overall idea of how good the fit is of where your control points are relative to where the original image is. How well did you actually point in the spot you were supposed to point to? This isn't hard, and maybe we'll do it as a demo if we can later. I always use like nice square states like Colorado or Wyoming, so I don't have to do a whole bunch of points. But you just bring in some random image from the web, and you can give it real world coordinates using georeferencing. Another huge aspect of ArcGIS Pro is the fact that they've actually gotten rid of what used to be called Arcscene. Arcscene was a separate program that you used to work with three-dimensional data in ArcMap, the old version. Now in ArcGIS Pro, all the 3D is built right into ArcGIS Pro. So you can actually look at 2D and 3D side by side. It's actually very cool. So 3D data is similar to 2D data other than it has height built into it as well as the X and Y. There's lots of different formats for 3D, and 3D is something that sounds really cool and you can do some really great things with it, but it's sort of more of an advanced technique that we don't cover much in this particular class. So something like you can have a DEM, you can drape imagery over that like a base map to give it sort of that rugged feel. You can use 2D features with a base height, and sort of extract out the building heights. And that's what you see in the bottom image there. Those are buildings, and the red dots represent sort of the tops of those buildings. And then the program calculates how tall they are based upon that Z value. You've heard me mention several times DEM, or what's known as a digital elevation model. It's a very common type of raster that uses, every cell value as being an elevation value. And just like anything else, you can use those to render them in 3D as well, making sure that you have, your coordinate systems all lined up and things like that. And you can do some fun things with 3D with DEMs, and plus you have all the ancillary stuff you can derive from DEM, things like slope and aspect and hill shades that you can also create in both 2D or render in 2D or in 3D. A new thing that's sort of been added to Arc Pro is what are called voxels. Now, we're not going to do a ton of this, but a voxel is a raster cell with a height encompassing a volume. So this is how you would start to model things like, water transport and stuff like that, where you have tiny little boxes of volumes and you can stack them together to create, sort of a picture of what's going on, both in 2D and in 3D with volume. Pretty cool stuff. I haven't done a ton with this yet. I hope to do a little bit more down the road. Then you have point clouds. Now, point clouds store millions of XYZ triplets. So you have to have all three. This is typically derived from what's called LiDAR, or light detection and ranging, that produces these cloud data sets. LiDAR has traditionally been flown with an airplane. So the airplane flies over, and there's a laser beam scanning back and forth over the ground, um, millions and millions of times a second, just generating a boatload of data. It's very, very compact data in terms of there's a lot of data per square unit. So this is where you can start to get sub-meter resolution. And you can see in the image here, everything in red is a height value. So you could see the bridge has been extruded to sort of give that height. All the buildings have been extruded, and then the color scheme is such that the blues still represent sort of the water surface. LiDAR is something that is, here to stay. It's awesome. It's gotten so much cheaper. A lot of it's being flown by drones now, which brings the cost way down. However, a lot of it is also proprietary. So people who have the money to fly this stuff, whether it be with an airplane or with a drone, have a tendency to hold on to it and keep it for themselves unless if you either work with them or you purchase it. But it's very cool data. I cover this quite a bit in the advanced GIS course, which will be offered in a year from now. You also have TINs, which are triangular irregular networks, which are sort of these nodes and triangular facets that allow you to efficiently store 3D surfaces with fewer nodes and flat areas. It's sort of a geometric way of representing 3D surfaces without all the detail. And sometimes you just don't need all that detail. And tins are nice that way, that they can give you what you need in terms of height values, high values, low values, what's going on, without all of the uh, being bogged down by the cumbersome number of, the weight of the file sizes. You can also derive other things from tins as well in terms of 3D modeling. You have what are called multi-patch features. I've done a tiny bit of this myself. This is where you start getting into building 3D boxes, so to speak, let's say buildings, not extruding heights. This is actual building shapes. Maybe some of you have heard of a program called SketchUp, which is free, I believe. Pretty cool stuff. You can start with, a lot of people start with that, and then they kind of bring that into GIS. This takes some practice. This is definitely an advanced feature. I've only touched on it a little bit. I took some data that John gave me and sort of a 3D model that an old grad student had done, and I took it and made it 3D so you could like rotate it in 3 dimensions. It was very rudimentary, but you get the idea. Another new feature that they have are what are called space-time cubes. I have no experience with this other than a tiny bit in a course I took online, but I got to tell you, these are very cool. So a space-time cube sieves XY points into regular grid and displays an attribute through time. So the height of each one of those cubes is not, let's say, let's say a higher elevation. It's newer in time. So the bottom stack is the oldest in time. So you're going through time, going up each one of those stacks. So if you look at this map, the map shows the sum magnitudes of earthquakes in space and time. So you can see that there were earthquakes where they are in a two-dimensional sense, that they're spaced out, but you can also from the 3D aspect of it show how much time, how many times, excuse me, how many times the the earthquakes have generated in one particular spot. So the higher the pillar, so to speak, the more earthquakes, or the higher the magnitudes of earthquakes, excuse me, because it's the sum magnitudes. The higher the magnitudes of those particular earthquakes, and then the dark purple shows where and when the shaking was the most intense. So you can kind of pick and choose an attribute. In this case, let's say intensity, and highlight those and to show where the highest amount of shaking was in time. So if you have, there's a couple like here, you see several. If you look at this one here, you see several over time of varying shades of purple. So that particular area over time has shook quite a bit. Whereas you have some other ones that barely have any purple, like let's say this one right out front. Oops, sorry, wrong screen. This one right up front. Ah, there we go. Sorry. So that one has very little high intensity shaking. That's probably partly because it's out in the ocean. So that makes sense too, or looks like it is, at least from that perspective. So these are really neat. We're not going to get into these in this class, but if you're doing any type of temporal relationships that vary over time, this is a very, very cool method to visualize that both in space and time. That's why they're called space-time cubes. Very cool stuff. And they're not that, as long as you have all the attributes, this isn't hard to do at all. You got to have your Latin lan, so to speak. You have to know where it is on Earth. Then you have to have an attribute that represents dates and times. And then finally you can take that a step further, and then if you have the intensity values, you can color them according to those. So you essentially need 4 pieces of information, XY place, date and time, and then some other value you can shade, let's say in this case, intensity. So to create one of these, you have to have a correctly formatted date time field. Um, this data contains earthquakes over a 36-hour period. So you have to fill all this out, and I'm not going to go into gory detail about this because we probably won't touch this too much. And then the output for this is what's called the standard NetCDF data, um, which is a universally recognized file format that's very useful for doing temporal analysis. So with Dr. Shangping Zhu, I helped him with some modeling for transevaporation rates, and he gave me some data, some NetCDF data. And when you bring it into GIS, you look at it and you see one image, but what you don't realize is that actual file has 365 snapshots, one for every day of the year, even though you only see one of them on the screen. So it's really neat what you can do. That you can iterate that through time and all kinds of neat stuff like that. Again, this is a very new feature for ArcGIS, in ArcGIS Pro. I never did any of this in ArcMap whatsoever. Now, one of the things about rasters is you got to get used to some of the file formats, and that takes a little bit of practice. It's nothing too serious. You have the file geodatabase raster, FGDR. Now, when they first came out with file geodatabases back in version 9 of ArcMap, the big debate was, should you store them in the geodatabase or store them outside? And is it is there harder to do analysis while it's sitting in geodatabase or outside? Well, I can tell you now, being that we're in Arc Pro, you definitely want to use and save your rasters in your geodatabase. It's at the point now where everything should just be stored in there. However, when you first download them, they're probably not in a geodatabase, and you have to kind of get used to some of the file formats, things like a TIFF file, which is an image file that's lossless. So there's no loss of resolution in there. It's not like a JPEG. It's the opposite of a JPEG. So these files can get very big, and they keep all of the information in there. You can zoom in on these. That's why they call them GeoTIFFs. You'll see the term GeoTIFF. GeoTIFF is a georectified TIFF, and you can find these online. ERDAS files, probably won't deal with that. That's a remote sensing. That's a remote sensing program. They have their own file type. Grid files, which you'll still see quite a bit. Those are sort of the default GIS, ArcMap, ArcInfo, going way back, file format that sits outside of a geodatabase. And then you've probably heard of a couple of these, JPEGs and maybe PNGs. I mentioned the Mr. SID files. Those are highly compressed proprietary format images, very cool. The .bil file, which is a binary interlaced something, or I forgot what it means. That's been used quite often by the USGS. Not a big deal. I usually got to look up how to manipulate them just because I forget sometimes. But I believe there is a tool in the toolbox that'll convert those now. And BSQ, I will admit, I have never heard of. I'll have to look that one up. Um, like I mentioned earlier, if you have a table of discrete values, let's say land use or something like that, that's in raster format, you can get uh, attribute tables. Now, with a continuous raster, for example, let's say elevation, there's way too many values to create. There'd be millions of them to create a row for each one of them, because each one is almost, every value is pretty much different. So if you have a table that with limited number of unique values, you can actually have an attribute table for a raster. Like I said, land use is the easiest one. For the soils, I believe will work as well. And so you have the value field. You can see that here, the value field, which is sort of the number in raster format that you could use for this, in terms of, like, it's just an integer number usually. So, but for our purposes from humans, we need something a bit more, which I'll get to in a second. You have the count field. Now, one of the things that you'll notice right away is in vector format. Let's say I have some polygons, some county polygons. When you open the attribute table for the county polygons, the area field is automatically generated for you as long as it's sitting in a geodatabase. So if I scroll all the way to the right in my attribute table, you'll see a field called shape_area. That field is automatically generated. We love it. That's what we use throughout our analysis, but that's not the case for rasters. Now in raster world, you'll get what's called the count field. Now the count field is the number of cells with that particular value. So for the value of 1, we have 29,190 cell counts with that value. So what you can do then is you can manually do the math to get the area of all of those values. So what you do is you take 29,190 and multiply it by the square area of your raster resolution. So if I have a 10 meter DEM, I'm going to multiply that number by 100. 10 times 10 is 100. If I have a 30 meter DEM, 30 times 30 is 900, so I'll take that count number and divide or multiply it by 900 to get the total area of all of the 1 values. So that's how you can get area from a raster. It doesn't automatically generate a field for you, but it does. You can calculate it yourself manually. So you can have explanatory fields. For example, you see the unit name with the alluvium and Now that's not what's going to map on your screen. What's going to map on your screen is the value field. That's what you're going to map. But what you can do is you can label it with the unit name. So you don't want to map 1, 2, 3, 4, 5, 6, 7. You want to map alluvium or this group or shale or whatever. So you're going to actually map by value, but you're going to label via the unit name. So that allows you to make, give your map more information than 1, 2, 3, 4, 5, 6, 7. And so for the last slide of this chapter, we have the concept of no data. So if you're new to this sort of thing, um, no data represents a special value used for some raster formats to indicate absence of data. That is very different than zero. Okay, please understand, no data does not equal zero. It means no data has been taken at that particular location. A great example of this is when I've dealt with soil data from the USGS, or excuse me, the USDA. Um, the pH values are often missing because of things like lakes and stuff like that. They don't take the pH of lakes, and stuff like that, because you'd have to average it over the whole lake. So you'll have these void values, which are no data values, and there's nothing you can do about it. There's a couple of different ways of sort of trying to make sure that that's there, that you can sort of average over an area, or you can have the program add zeros or add null values or whatever there's a couple of different ways, but that is not the same thing as zero. So, for example, zero is a valid precipitation measurement, meaning it didn't rain. Whereas that doesn't mean nothing was collected there, it just means it didn't rain. Okay, so you have to know the difference. Sometimes in rasters, you'll see things like minus 999 or minus 99999, or how many other nines they want to add. So these are these big values that you have to understand. As soon as you see those, oh, those are no data values. And sometimes when processing rasters, you have to void those out with things like selection techniques and stuff like that. That takes a bit of practice. The final thing I want you to get off this slide is that rasters are always rectangular. Regardless of what you see on the screen, they're always rectangular. That is a function of the programs that were written to manipulate rasters way back in the day required squares, okay? So even if we sort of clip a raster, which we'll talk about later, if we clip a raster, you could see it in the image here. This is South Dakota. It has sort of this irregular shape here. Even though you don't see anything around it, the actual program is squaring off this raster. Okay. Visually, we don't want to see the square, but you just know that computationally it is there. So it's something you have to be aware of. Um, that's just, again, goes back to the nature of how the programs were written, probably easy to keep things easy, the math easy, but rasters are always rectangular. Wow, okay, so that's the end of chapter 6, right? So she, like I mentioned at the end of chapter 5, she kind of plucked out chapters 5 and 6. Those are new to this particular book. And I like that the rasters have been, and vectors are kind of been separated. It makes talking about them a bit easier, kind of focus in on one or the other. I am very partial to rasters because it's just the bulk majority of what I do. It's what I enjoy. So you start to learn these techniques over time. None of this is that hard. It just takes a bit of practice and understanding some of the data formats, and then how to manipulate them, and making sure all your sort of I's are dotted and T's are crossed with things like environment variables, cell size, projections, which a lot of that is the same. It's just as applicable to vectors as well. So we will use rasters more and more as the semester goes on. Um, and the same rules apply. You got to make sure that you're not in Latin lawn. You're projecting things. You're using the correct resampling method. Nearest neighbor for discrete rasters, or bilinear for continuous rasters. You want to keep all that stuff in check. Your cell size values. So when you go to do your actual analysis, you know that the outcome is going to be, at least plausible, although it'll always be non-unique. All right, so that's it for chapter 6. So the next chapter, we're going to kind of bounce back into vector world with attribute data. And the attribute tables, whether they're in vectors or discrete rasters, that's where all the data is, right? That's where you can start to see patterns or figure out what questions you need to ask to hone in on the data that you need for your particular analysis. So the attribute, there's a ton of things you can do in the attribute table, and I will see you in chapter 7. Take care.